All right, so this is the final version of our Consortium Tuner project for Sludge team. And so the goal and motivation of the project was to translate real genetic circuits from sludge environments into a configurable simulation platform, allowing users to design ecosystems and assess their stability before implementation. And so the reason that this is relevant to us is that for Johnathan's company, basically they co-culture E. coli and geobacteria to enable stable electric power. And these reactors are deployed in breweries and food processing facilities. However, the performance is limited by biological instability, which makes them very difficult to take care of. So the key innovation that we wanted to try to take advantage of, or to enable people to take advantage of through our GUI, was to introduce obligate cross-feeding to prevent competitive takeover, community drift, and emergence of cheaters. And so this immediately makes the problem go away if you can come up with a consortium that works well, and it makes it so that they essentially maintain themselves. For the functionality, there's a GUI with 6 adjustable sliders that you can change to adjust the functionality of the circuits and the populations for the consortium across these different bacterial populations. You have these things are mapped to ODEs that we got from literature, and so you can run the ODEs run live, and it enables rapid exploration of how circuit combinations affect ecosystem behavior. And so you can see this is the GUI. We'll go over this a bit more later. For the specification, all of them need to be from sludge environments. They need to be defined interaction categories for cross-feeding, metabolite production, dependency, stuff that would help out with that self-regulation that we talked about earlier, and with electricity production. The system must support modular selection and combination of multiple potential circuits, and some of the constraints are that it must be good for real-time use. It must require very little technical knowledge. It must be defined based on these predetermined categories and on literature-supported interactions. We created this literature review to create, along with these Knox circuits, and we used the Knox circuits and relevant ODEs in the literature review to make an XML file to run the simulation in iBiosim as a basic prototype idea. The parameters that we adjusted were cross-feeding, so how much mutualism there was, the kill switches, so how much, like the levels of kill switching in the populations, the electroactivity, which is the electrical current in the being driven, nitrification and denitrification for maintaining nitrogen levels at optimal amounts, production for metabolite production, and quorum sensing, so coordination based around cell density of the solution. We uploaded these XML files to iBiosim and manually verified that the results made sense. We had this whole system of interactions, and so the circuits were based on SBML file inputs. There was a reference table. There were defined concentrations for each condition. Basically, we had this Jupyter notebook that ran as a standalone simulation based off of our ODEs more completely. So for the user interaction, we had the sliders and this weight vector. We had our predefined genetic parts library and the ODEs. We used the scoring engine to select the consortium and then we put that into our visualization layer with a consortium table and a time series plot to make it clear to the user how it worked over time. And this is the demo.
All right, so this is a quick overview of it.
Hold on a second. All right, so this is a quick overview of the Consortium Tuner. This is the final version for the project. Here we have all of these concentrations of all the different species that we are looking at. And which species are we looking at? Well, we go up to the species picker and we can select different species that we're interested in. So let's say I wanted to look at this preset. We have a couple presets here. Let's look at this preset concentration, these preset relative concentrations for nitrogen cycle and nitrogen fixation. So let's remove all these things that we don't care about at the moment, and we can look back at them later. But let's just hide them all for now. And you can see that over time, you can see these nitrogen species go to into because of these species down here, and it's showing basically the relative concentrations of all these different groups and what species you might be interested in. And let's say, I like this consortium, I want to try to build it out, and there's like a couple that we don't really care about, so we're going to call these out. So these are the only ones we care about, and then we can go down here, and we have these circuits down here that we can use as the basis for our gold bar, and we have a quick little ecosystem summary, and yeah, that's about it. And so for our successes and failures, this is obviously a very nice, accessible design, very simple to interact with, and there is a good amount of grounding based off of the ODEs that we implemented in the design and we manually verified. However, ultimately, it just couldn't be that complex of a model. There were certain limitations to the data we had, and there's no standard model to work off of, so we didn't necessarily know how reasonable our design was. And so ultimately, we probably could have improved this if we were able to manually test designs and then use that to verify our consortium selector, and then we could manually curate the different rules better, and just hone in a little more on something a lot more specific. And thank you.